The aim of this video is to gain an understanding of what is meant by an inverse matrix and how to find the inverse of a matrix in certain cases. Let's first of all consider integers and the word reciprocal. What is meant by the reciprocal of an integer? Well, we know that a reciprocal in the case of, say, 3 would be 1/3, and we can express that as 3 to the negative 1. One of the properties of a reciprocal of a number is if you multiply it by the original number, you get a result of 1. We could also describe 3 to the negative 1 as the inverse of 3. And when we're talking matrices, if we multiply a matrix by its inverse, whilst we won't get a result of 1, we do get the equivalent for matrices, which is the identity matrix. It is important to note, though, that like with numbers, we should be able to multiply these matrices in either order. In other words, m multiplied by m to the negative 1 or m to the negative 1 multiplied by m, and in both cases get the identity matrix. For that reason, both the original matrix and its inverse are both square matrices. Let's have a look at a 2 by 2 matrix expressed as A, B, C and D. There is a formula to work out the inverse of this matrix, and it's 1 over the determinant, which is AD minus BC, and the resulting matrix has the entries D, negative B, negative C, A. There is another video on the You Do the Maths YouTube channel which goes through the process of how this formula is actually determined for a 2 by 2 matrix. Let's have a look at an example and see how we work out the inverse matrix using this formula. We can see here our matrix X has entries such that A is equal to 1, B is equal to 4, C is equal to 1 and D is equal to 5. Let's substitute that into the inverse formula to see what result we get. It might be a good idea to pause here and do your own substitution and see if you get a matching result. So substituting the values for A, B, C and D, we can see that in the matrix for the inverse of X, just ignoring the fraction for a moment, we have 5, negative 4, negative 1 and 1. Notice how the values in the leading diagonal, that's the one going from the top left to the bottom right, have been swapped, and the values in the other diagonal have just changed sign. Now the determinant, which is on the bottom line of our fraction at the front of the matrix, turns out to be 1. So effectively we're multiplying the values in the matrix by 1 over 1 or just 1. So once we have the result for our inverse matrix, we can check it. We can multiply x by its inverse or the other way around, the inverse by x. And in both cases we should get the identity matrix. Now the inverse matrix formula is relatively straightforward for a 2 by 2 matrix. It's not so the case for matrices of increasing dimensions. Nonetheless, let's have a look at an example involving a 3 by 3 matrix. In this case we have two matrices, E and F. And the first thing that you'll be asked to do here is to determine the product of those two matrices in the order EF. So it might be wise to pause here, see if you can do the multiplication and check to see you agree with our result. When we perform that multiplication, we can see that the product EF has 4's running down the diagonal and 0's elsewhere. So effectively that's 4 multiplied by the identity matrix. So we'll keep that in mind for later on. Let's now look at a related problem. Let's assume we're being asked to solve this series of simultaneous equations for 3 variables x, y and z. We can write these equations in matrix form. We've got E, which represents the coefficients in the equations, x, which represents the variables x, y and z, and n, which represents the constants or the values on the right hand side of our equation. We can express this in product form, Ex equals n, and it might be wise just to stop here and check to see that you agree that if you multiply the matrix E by x, you do get a 3 by 1 matrix which happens to match the left hand side of the equations we just saw. Now that we have our system of equations in matrix form, we can solve this using matrix algebra. And what we want to do is isolate the x, in other words, remove the e. By isolating x, we'll be able to find our unknown values x, y and z. So when we're solving an algebraic equation, what we want to do is divide by a value to remove it. But using matrices, what we do is multiply by e to the negative 1. That's the same as multiplying by the reciprocal of a number. But of course we have to do this to both sides of the equation, and we need to do it to the left-hand side of both of these expressions so that we can match the e to the negative 1 and e on the left-hand side of our equation. Now when we do that, we know that multiplying an inverse by a matrix will end up being the identity, or effectively like 1. And that means our left-hand side becomes x, and our right-hand side is still e to the negative 1 multiplied by n. So all we need to do now is work out the inverse of matrix E, which is going to be a 3 by 3 matrix, and multiply it by n, which is a 3 by 1 matrix, so we will get a result. The only trouble is, how do we find the inverse of a 3 by 3 matrix? Well, this matrix E matches what we saw beforehand when we multiplied E and F together. When we multiplied E by F, we got a matrix that we said was 4 times the identity matrix. It's got 4s running down the diagonals instead of 1. So what that means is, if we can multiply F by a quarter, what will happen is we can also multiply our result by a quarter, and we end up getting the identity matrix. So what that means is, the inverse of matrix E is 1/4 of matrix F. So going back to our problem where we're trying to solve for the unknowns, we needed to multiply e to the negative 1 by n. Well, the inverse of matrix E is 1/4 of matrix F. And when we complete that multiplication, we get that x is 1/4 of the column matrix 24, 12, and negative 24. And multiplying that constant through, we get our solution for our unknown values as 6, 3, and negative 6.